Okay, this current series of lectures is going to be taking a look at Newtonian mechanics, and suppose we should start with Newton's laws of motion. Now, it should be clear that this is a model that Newton came up with in an attempt to provide some sort of a mechanism for experimental data that was being observed. And he came up with three statements. And every book tries really hard to restate them very clearly and whatnot, but I find it's usually best to just go back to the way that Isaac Newton himself stated it in the Principia, minus the fact that he wrote it in Latin. So with that, we'll take a look at the first law here. So says that every body continues in its state of rest or of uniform motion in a straight line unless is compelled to change that state by forces impressed on it. Okay, this does a few things. First off, it says it's the natural state of affairs for something to go in a straight line at a constant speed forever. It also implicitly defines the idea of a force by saying it's that thing that changes the motion of an object from its natural state of affairs of moving in a straight line at a constant speed. A little more subtly, it also brings in the notion of inertial frames, but I will get more into that in a moment. Okay, now let's take a look at the second law. It says the change of motion. Okay, that term now, we would now say the change in momentum is proportional to the motive force impressed and is made in the direction of the line in which that force is impressed. Okay, so in math terms, we would write that as saying F net equals dp dt. All right, and then finally, for the third law, when Newton first wrote it, he only wrote this much of it right here. To every action there, oops, I should say there. To every action, there is always imposed an equal reaction. But that wound up creating problems, as it kind of gives the false impression that perhaps first one force acts and then the reaction force happens. It's just an unfortunate way that English works. So in later editions, Newton added the bit after the semicolon saying, or the mutual actions of two bodies upon each other. So the keywords here are the key bits here are mutual and upon each other. So instead he's saying that when two bodies interact and they exert forces on each other, they exert those forces simultaneously. They'll always be the same type of force, they'll always be the same magnitude, and this contrary parts line means they'll always be oppositely directed. So in math symbols we would, we would usually write the third law as something like the force of 1 on 2 is equal to the negative of the force of 2 on 1. Okay. So now let's revisit the first law just a bit more. In the Newtonian framework, and we'll visit other frameworks later, we'll take a look at D'Alembert's framework for mechanics later. But in Newton's framework, the only quote-unquote valid frames of reference that you can use are those that move at constant velocity. So, let's think about what we mean by that. So let's say, as we like to do, we're in a train car and we're observing a rock being dropped. So we're outside the train car. So the rock is being dropped outside the train car. So that's the first position of the rock. And here we are in the train car seeing the rock like so. Okay, now let's say this train is speeding up. So at some time later, in the frame of someone standing by the tracks, the rock might say be here, and the train is now there. And then a little later yet, let's say the rock is here, but now the train is like that. And I tried to draw it so that there's more space here than there. So in the perspective of someone in the train, when they're looking at the rock, here's my train car. So I look out the window at the rock, I would be seeing the rock move. Here, let me change the color there. I would be seeing the rock move something like that. So we would be taking some sort of a funky trajectory. Now, in addition to seeing a force of gravity down, like so, I didn't get that last dot in right. Let's try that again. More like this maybe. So trajectory looking something like that. So in addition to seeing a force of gravity down, which they would both agree on, the observer in the train would have to conclude that there was some other mystery force. We call these fictitious forces, and we'll get into them later. But for now, we'll just leave them alone and say that we can only do mechanics in an inertial frame. Now, the book gets into quite a discussion of what even constitutes an inertial frame. And the best definition we have at the moment is moving at a constant velocity with respect to the cosmic microwave background radiation. Okay. Now, to look at the second and third laws, I'm going to, bring in an idea due to Richard Feynman. He was attempting to come up with some way to think a little more about the second and third laws, see if he could simplify it out. And the way he did that was he came up with a definition of mass that is not the official one. He had what's called the Recoil definition of mass. Now, if you remember from previous courses, the way we operationally define mass is that thing that a balance measures. Now, that, strictly speaking, is what we call the gravitational mass, which is a measure of how strongly the Earth's gravitational field interacts with something. So its gravitational charge, if you will. We also talk about the inertial mass, which is the m in F equals ma. It characterizes how hard it is to change something from moving in a straight line at a constant speed as it wants to do. Feynman was more focused on the inertial mass, and so he came up with this thought experiment. He says, let's imagine we've got like a perfectly smooth hockey rink or something like that, and we stick two masses here, M1, M2, and we imagine sticking in a compressed massless spring in between them. And then we just let the spring go. Okay. Well, at some later time, we'll have my mass M1 moving at V1 and my mass M2 over here moving at V2 like so. And he proposed defining mass in a operationally defined mass by saying that the ratio of M2 to M1 was equal to the, we have to use absolute values here, well, no, or what we can just say is equal to the speed V1 over the speed V2. Now, to put something onto standardized footing, we can imagine doing a daring commando raid in France and stealing the international prototype kilogram, making that mass M1, and then we can set everything else from there. Now, the reason why we're not totally happy with this is that it breaks down a bit in relativity. It turns out in relativity, it only really makes sense to compare masses when two things are in the same frame with respect to each other. So in other words, they're at rest. So the only time we ever compare masses officially, at least relativistically, is when the two masses are at rest with respect to each other. Now, what this is really giving us here, if we worry about relativity, so I'll just put this in as a little side note here, is this is giving us the ratio of gamma 2 M2 over gamma 1 M1, and that's equal to my V1 over V2. Now, you'll find some books, because the Feynman definition of mass was a really good idea, just didn't get all the love it deserved. You'll find a bunch of books, especially say from the 50s to the 70s, that absorbed these gammas into the m's. So if you've ever heard anyone say something like, the faster something goes, the more massive it gets, that's because they're using Feynman's definition of mass rather than the one that we currently accept. Now, in this class, that's not really going to matter. And that's because we're going to keep everything at very non-relativistic speeds, so our gammas are basically 1. And so we can get away, so in that case our recoil definition of mass is consistent with the definition of inertial mass. So we can rearrange the definition a bit, and we can put it into vector form. So we can say, all right, the change in my quantity m1 times v1, that'd be equal to the negative of the change of m2 v2. So that's just rearranging Feynman's definition of mass here and looking at the change in terms of the before and after in the recoil. Okay. Now the minus sign here is just simply because one of these is going to the right, the other one's going to the left. Okay, so if we follow this through into the land of differentials, this would mean that ddt of m1, of m1 v1 would be equal to minus ddt of m2 v2. Alright, but these mv's here, That's the linear momentum. So the linear momentum, P is defined to be the product of m times v. And this is again a non-relativistic definition. If we're going to do this relativistically, we got to stick a gamma in front of the m, but in this class we're never going to go that fast. So then, like I wrote before, the second law is F equals dp dt. And if we follow on from what we had just looking at the recoil definition of mass, we realize here that we've got a ddt of p and a minus ddt of p. So this gives us the third law, like I presented, that the force of 1 on 2 is equal to the negative of the force of 2 on 1. Okay, now something that we do have to take some care with. Although we're neglecting relativistic factors of gamma, we are going to allow for the possibility that the mass of the system could change. Rockets are a notorious example of that. So if we look at our F equals dp dt, that's ddt of mv, right? So we have to do the chain rule on this. We're going to get an m dot to v plus an m a. Now, in most systems that we look at, unless they're rockets or raindrops or something like that, where the mass could change on us, usually m dot is 0, and this term goes away right here. But in the general case, say if we're launching a rocket, the mass is not a constant, and we have to factor that in. Basically, we'll see that'll have the effect of looking like it's an extra force. Okay, now if we go back to our recoil, the result from our recoil definition of mass, one of the things that we got that dp1 dt is equal to minus dp2 dt. So we had that as the third law, but now let me just rearrange this. Let's just add the two terms, add the dp2 dt to both sides. So in that case, I'll get ddt of p1 plus p2 equals the null vector. So that means that the time rate of change of the sum of the momenta, one momentum, two momenta, the time rate of change of the sum of the momenta is 0. So that forces the sum of the momenta, p1 plus p2, to be some constant vector. So if our system is isolated, the total momentum of two interacting bodies is a constant. But this does require an isolated system. So that means no net external force acting on my system. That's to keep it consistent with what Feynman was looking here. Sure, there's a normal force and there's a weight, but they cancel, so there's no net external force. The system is isolated. Okay, so let's just do some quick examples of that just to remember how that works. First example, you probably remember from your previous courses. Let's just go fire a bullet, mass little m, initial velocity v0, into a big block, so mass big M, and initial velocity big V0 is 0, so we're at rest. Now, afterwards, what will happen is the bullet will embed in the block, so the combined mass of the combined system is now m plus m. We want to know what the final velocity is. Well, this is great. There is no net external force in the system. So because of that, we can demand that the final momentum equal the initial. Well, finally, it's going to be the mass of the combined thing, m plus m, times v, and we're just looking in the x direction here. And initially, well, this guy's at rest, so the only guy contributing is the bullet, so that'll be mv naught. So we get that v equals m over m plus m v naught. And you should ask yourself, does this make sense? Well, first off, the units check, meters per second, kilograms here, kilograms there, they cancel, so yep, life is good. And the other thing is does this obey your intuition? You would expect the combined object to be moving slower than the bullet. Well, the bullet is very light, the combined object is very heavy. This will be a number much less than 1. And so yes, indeed, we get that the combined object is moving slower than the bullet. And also, it's moving in the same direction as the bullet. There's no minus sign. Okay. So that was a simpler example. Now let's go ahead and take a look at the more complicated example. Let's launch a rocket. All right, so we'll assume that we're far enough, that we're in deep space, so we don't have to worry about the gravitational influence of whatever planet. And we'll say that the mass of the rocket at the moment is m, and it's going at speed v at the moment. Alright, so here's my rocket motor here. We're going to have exhaust coming out of the rocket like so. At any given moment, the mass of that exhaust will be dm. Okay. Actually, strictly speaking, it'll be a minus dm because dm is going to be referring to the change here, which will be negative, but we'll work that out in a moment. Slightly confusingly, we're going to have the exhaust moving forward, and we'll stick in the minus sign later. And this is measured relative to the rocket. Okay, so what we're doing here is we're going to be getting the first rocket equation, which is due to Solovsky, the Russian father of rocketry, who frankly probably made greater contributions than the American father of rocketry, Robert Goddard, although I think they're both really cool guys. So let's go take a look here. So initially, our total momentum at some time t would be equal to the mass of the rocket times v. And we're going to look at some small amount of time later dt. Remember, physicists usually treat differentials as just really tiny deltas. So at some time t plus dt, the mass of the rocket is now m. Whoops. The mass of the rocket is now m plus dm. And yeah, I know dm is negative. We'll deal with that in a moment. And the speed of the rocket is v plus dv. And to that, we have to add in the mass of the ejected fuel. The ejected fuel has a mass minus dm, like so. And since we're working in this stationary frame here, the fuel was going forward at speed v to begin with, and then we have to subtract v exhaust. So this will be going at v minus v exhaust. Okay, so let's just go ahead and multiply it all through. So we can do FOIL on this guy here. We get mv, so it's first, outer, plus mdv, inner, plus dm times v, last, dm dv, minus, we'll have a dmv here, and a plus dmv exhaust. Okay, we'll take our favors where we find them, and right here we see that those DMVs cancel, so we're very happy about that. Okay, the other little cheat, the other things we can look at here is we can observe. Actually, let's cancel those a little more authoritatively. Much better. We can also observe that this MV is just our P at time t. And come on, multiplying two differentials by each other, that's approximately 0. Okay. So to get my dp, that'd be equal to p at t plus dt minus p at time t. Alrighty. So what we've got here is p at time t plus mdv plus dm times v exhaust minus p at time t, and those cancel. So we've got our dp. Now, if there's no external force, our dp is 0. That's why we did this way out in outer space. Alright, so this finally gives me, and I will cryptically label it double star, mostly because I need to get back to it. This gives me mdv is equal to minus dm times v exhaust. And then if I want, I can go ahead and turn those into mdv dt equals minus dm dt v exhaust. So I can finally express this as mv dot equals minus m dot v exhaust. Okay. Now this minus m dot v exhaust, we look at the left side and say, hey, that's an MA, so we expect this to be a force. Now it's not. It's really due to just the fact that the rocket is losing mass in a hurry, and it's ejecting that mass. So we can interpret this as the force acting on the remainder of the rocket, and we would interpret this actually as the thrust. Okay. So taking our, taking our double star from before, we can rearrange that a bit. We can get dv all by itself is equal to minus dm over m times v exhaust. Okay. And then I can integrate both sides. I can integrate this from, v naught to v. And I can integrate this from m naught to m, keeping in mind that m will be less than m naught, because as we burn up fuel, the rocket is getting lighter. Alright, so times v exhaust. Okay, so when we do this, we get that v minus v naught equals v exhaust times the natural log, and you'll probably eventually start seeing me just write log for natural log, so if I do that, it's the same thing to me. It's natural log of m naught over m. So there's a couple of things that we can get out of this. To get going quickly, you want to have a large exhaust velocity. So this also has the advantage of making m dot a very large negative number. So in other words, the faster you get rid of your mass, the better. So that gives rise to the old joke, what's the difference between a rocket and a bomb? About 2 minutes. Meaning that really firing a rocket is more of a controlled explosion, and we're just making it happen not quite as fast as a regular explosion, so that hopefully it all survives in one piece. The other thing that we can see out of this is that as far as the top speed goes, the top speed depends on the exhaust speed, but also depends on the masses here. So this is why you see rockets get staged. So for instance, if you take a look at a typical rocket, the payload is probably just in a little capsule like this, and you got like a second stage here, then maybe a much bigger first stage here, and you burn the fuel from the first stage, and then you eject the first stage and make it go away, and then the rest of the rocket goes on. Now, why the heck do we do that? The reason we do that is that this allows our m naught over m. Once we've expended all the fuel in here, we're just carrying dead weight right here. If we can get rid of that, that transforms m naught over m to m naught minus, we'll call the mass of the rocket of the first stage delta m. That replaces the numerator by m naught minus delta m, and replaces the denominator by m minus delta m. So if you think this through, you'll realize that this is a bigger number than that is. So when I go and stick it in here, I can end up with a bigger final speed for the same amount of fuel that I'm expending. Okay.